Hello folks, today it is a third of magnetism, third lecture of magnetic field, let us say, and the topic that I have is force experienced by a current carrying conductor in uniform magnetic field. So previously we discussed about how we can draw the field lines of a straight current carrying conductor, and now the same current carrying conductor, when we place that in uniform magnetic field of others, some other things, maybe it's a solenoid, maybe it is used magnets used in automobile industries or like that. So when you place it like this, what happens? So as the title goes, it experiences a force. So where that force comes from, we'll be discussing. So that requires first to draw a diagram. So I have two diagrams here. One is before and one is after, as you used to share photos in Facebooks or like that, before, after, 10 years challenge and so on. So I have got two magnetic poles here. So this is N pole of a certain magnet, and I have got this S pole of certain magnet. Maybe it's a two pole pieces of a horseshoe magnet. And here I place a conductor which is carrying current in that direction. So this thing is carrying current in that direction. Now what I have here is, I have got magnetic field lines due to this N and S. So let me draw a few field lines. Let me draw 4 of them. 1, 2, then 3, and then 4, and then 4. So it is slightly protruded here. I will correct it. So 4 field lines of this, I have tried to make it as uniform as possible by making them equally spaced. Now I have got a field lines due to this conductor. It is circular. So we have got one circle here, we have got another circle here, and we have got another circle here. So altogether 3 circles I have drawn. It is not necessary to always draw 4 circles. It depends on my choice, my mood, and my requirement whatsoever. So what will be the direction of those field lines? So that requires this application of this law, which is right hand thumb rule. So current going here, this rule. So it should be like this, 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 like this. So here like this. This belongs to this. Next is like this. Now these two magnetic fields. Now you must know that field lines never cross each other. Field lines never cross each other. So they will not cross. What happens is they interact with each other and they give a resultant. They interact with each other and give a resultant. So to draw the resultant, let me draw another diagram here. So the diagram should be like this. So this is the N pole. This is the N pole. And let me fix the separation here. Separation somewhat like this. So this is the S pole here. The S pole over here. S pole. I have the conductor here. Conductor. Now, what happens due to the interaction of these two things? So that depends on locations. So what happens is, in this location, both of these field lines are in same direction. So that means they add up. They add up. They influence. They motivate each other, or they strengthen each other. And in this region, what happens is they try to deduct each other. Here they try to deduct each other. So deduction, deduction. Here also deduction, and here they add up. So if so, what happens now is, it is trying to go like this, trying to go like this, but as it goes nearer to this wire, the field of this wire gets stronger. So it is led like this. It tries to go like this, but this thing will influence it like this. And so what happens is, the field lines coming here, the field lines emerging from here are led to go somewhat like this, because as it goes nearer, it is heavily influenced by this, because the distance here is shorter. So because of that, it has to go like this. And similarly, we have got this thing. So this thing will also somewhat bulge like this and like this, and this thing also somewhat bulge like this and like this. And what about this thing? So this thing is heavily influenced by this, and and what might happen is, it might just go side by like this, heavily influenced, but side by. So what we have is, here there is deduction. So reduction means that the field number of field lines is less here, and here it is addition. So addition means we have got more field lines here compared to this. So here cancellation, deduction, going against one another. Here it is addition. So we have got more field lines in this region and less field lines in this region. So let me draw the arrows here. Now what happens after this? Now what happens now is, whenever there is a great deal of magnetic field lines, that means it has got high magnetic field. And high magnetic field means that, as we have already discussed, magnetism is because of because of rotation. So here the magnetic field was less before, now it is high. High means that there is a rearrangement in the rotation of the electrons. Rearrangement. So here we are undergoing rearrangement of the rotation, direction of rotation of the molecules, and here there are no rearrangements because magnetic field is almost zero. So when we have rearrangements, what I mean is there are disturbances. You can realize whenever we are going to rearrange something, at that time there is the highest degree of disturbance. Hope you realize that. So let us say I want to clean my room. Clean my room means that I want to put it in order, but the process of putting in order is very random, is very disordered. So here also we are undergoing rearrangement in the rotation of the charged particles in the different atoms here. So here we have got large disturbances and here less disturbances. So what happens then? There will be a certain force. They will generate a force from large pressure region, disturbance region, to the less pressure region or less disturbance region. So that's why it experiences a force in this direction. So you can relate it like this. I am standing here, there is strong wind from here, but no wind here. So what happens? I might go somewhat like this, or my shirt will become like this. My hair, had it been here with me, so it will go like this, and so on. So here also, high pressure region, high disturbance region, less disturbance region, so there will be a force like this. So this force is called as Lorentz force. So it is called as Lorentz force. So the spelling is TZ at the last, but they pronounce it as Lorentz force. So it's okay. Now some people say, so because of gravity it comes down. No, it's not because of gravity. It's because of the force generated by the interaction of the two magnetic fields. Now, Lorentz force is there. So now if I reverse the direction of something, maybe I reverse the current. So if I reverse the current, what happens? So in that case, the figure will be also reversed. So what I do is, if I reverse the current, it will be like this. It will be like this. Then all the direction of these arrows will change. Direction of arrows in the circles will change. Circles will change. So what happens now is, I'll have to reverse all of them. So current coming like this. So it is like this, then like this, one more, like this, and this. Now in this case, what is happening? At the lower side they are adding, and at the upper side they are cancelling. So the field lines will be somewhat like this. Let me draw it. So it's not much difficult to draw once you know this. So at the lower side it will be somewhat like this. So what happens is, it will come like this. Yeah, it will go like this, and it will go somewhat like this. So this is the field lines. Now what happens? Crowd here, more interactions here, more disturbances here, less crowd here, all less there. So high pressure, low pressure, force will be in this direction. So Lorentz force will be in this direction. So in order to determine the direction of Lorentz force, there was a law by Fleming, which is called as a left hand rule. So according to his rule, what he says is, if this finger, the index finger, shows the direction of the external magnetic field, if this shows the direction of the external magnetic field, so N to S, so NS we have to point like this, and if this shows the direction of current, direction of current. So let me correct it. I still have not corrected it here. So right now it is the current is coming towards us like this. So if the wire shows the direction of current, so this should show the direction of current. So current here, direction. This gives the direction of the force the wire experiences. So let us try it here. So NS, it goes like this. Then the current is coming towards the observer, towards this camera screen. So current like this, and force here, force here. So if you go to the previous figure, at that time current was going like this. So it means current was going like this, and force down. In the previous figure, you might have noticed. So this Fleming's law helps in determining the direction of force obtained as a result of placing a current carrying conductor in a uniform external magnetic field. So this is called as Fleming's left hand rule. It's just a technique. It is not of mathematically not of much significance, but it's just a technique to find the direction of force. So we place the fingers like this. Some of you might do like this, but I do like this. So just I feel it very simple. So there are some people who cannot stretch their fingers properly. They might do like this, but still the oral format is this. So you either do like this or this. That doesn't make any difference. So anyway, this is the direction of the external magnetic field, N to S. This is the direction of current, conventional current, and this will be the direction of the force experience. And you can do like this. Want to remember, you can do like this, or you can do like this. You can do like this. You have to do like this. Stretch things like this, as if a ball has been placed here. Something has been placed here, somewhat like this. So you have to do stretch fingers like this and apply this law whenever you have to find the direction of force or direction of anything else.